After discovering electrons, J.J. Thomson was aware that there must be another particle in an atom. Why did he think so? Well, atoms are neutral. Atoms are neutral. And electrons are negatively charged. That means in an atom, there must be some other particles that are positively charged. J.J. Thomson was already very old. He was very close to retirement. But he wanted to see this study through. So he proposed what he thought would be the model of an atom. What he thought an atom would look like. That model is called the Plum pudding model of an atom. What that model is all about is simple. He said the electrons have a certain mass and they are finite. However, the positively charged particles that would balance out the charges on the electrons, he said those positively charged particles are like a cloud of matter that would balance out the electrons' charges. But the positively charged particles, they are not really finite. So they do not have any specific mass. That was J.J. Thomson's idea. And to prove that he was right, he enlisted one of his students, one of his PhD students, a very smart fellow named Ernest Rutherford. He charged Rutherford with a project that will prove that the Plum pudding model was correct. Rutherford was a very smart student. He proposed an experiment that would prove that his boss, J.J. Thomson, was correct. But he actually ended up proving that his boss was wrong. Let me briefly walk you through Rutherford's thinking. Rutherford was basing his experiment on the fact that his boss said an atom is simply made up of negatively charged particles and a cloud of positive charges. This was the thinking of Rutherford. Rutherford thought if he could fire something that is very heavy at an atom, he would expect all the particles that he fired to pass through an atom because electrons are really, really light. They are about 2,000 times lighter than the lightest atom. Think of it this way. If somebody gives you this project, prove to me that a piece of paper is not very thick. Prove to me that a piece of paper is not very thick. And you dream of a project that will look like this. You made a big screen of paper and you drove Walmart truck at 100 miles per hour through the screen. Your expectation would be that the truck should pass through the screen made of paper. That was the idea. Alpha particles are very heavy. They are about 7,000 to 8,000 times heavier than electrons. So even if the alpha particles collide with electrons, they will just knock them over and continue to move through. So this was what Rutherford was expecting. He was expecting that if I fire alpha particles, the alpha particles are like the Walmart truck, and I fire them at any atom, then the alpha particles should pass through unhindered. In reality, what he got is not what he expected. So he found a source of alpha particles. We're going to learn later about alpha particles. He found a source and he fired alpha particles at a thin gold foil. Again, his expectation is that all the alpha particles should just pass through. Well, most of the alpha particles actually passed through like he expected. Most of them. But a number of them were deflected at an angle, as if they collided with something and it got them deflected. That was actually not the surprise. The surprise was that some of the alpha particles were bouncing back instead of passing through. And because of that, Rutherford was thinking that there must be at the center of an atom something that is dense. And that thing, when alpha particles collide with that thing, they can bounce back or they can get deflected. That dense center is now what we call the nucleus of an atom. But that was not the only thing that Rutherford proposed. This is another thing that Rutherford proposed. He said inside the nucleus, you have the positively charged particles that his boss, J.J. Thomson, wrongly thought were clouds of matter. No, Rutherford said that is not correct. He said that protons are finite. They exist and they can be found inside the nucleus of an atom. And he proposed this very simple statement. For an atom to be neutral, the number of protons in the atom must be exactly equal to the number of electrons in the atom. I need you to remember this. This is very, very significant. So, for an atom to be neutral, the number of protons in the atom must be equal to the number of electrons in the atom. But there was still one thing that Rutherford himself could not really explain. And the problem was that if protons are actually positively charged and they all exist inside the nucleus of an atom, how come the positively charged protons are able to be in close proximity? How come they are so close to each other? Because the law of nature says that like charges must repel. It took about 25 years, but one of Rutherford's students, when Rutherford also became a professor, one of his students named James Chadwick was able to prove that protons are not the only occupants of the nucleus. There is another atomic particle inside the nucleus. Those particles are called the neutrons. So inside the nucleus of an atom, you have the protons and the neutrons. Both particles are inside the nucleus of an atom. Neutrons, according to James Chadwick, neutrons are neutral. They have no charge. And because they are neutral, they are able to separate the positively charged protons from being too close to each other. So imagine if my simple cartoon here represents the protons and the neutrons. The neutrons have no charge. They slide in between the protons to prevent the protons from getting too close. And that is how the nucleus of an atom happens to be stable. These are the conclusions, the summary of the conclusions from the Rutherford's experiment. Most of an atom's mass, and I will talk about that in a moment, and all of its positive charge exists in the nucleus of the atom. Most of an atom is actually empty space, and in that empty space you have electrons dispersed. And by having equal number of positively charged particles and negatively charged particles, an atom will remain neutral. So in a nutshell, we can represent an atom like this. This is the nucleus. Inside the nucleus, you have the protons that are positively charged. I'm using this symbol to represent protons. And inside the same nucleus, we have the neutrons that are neutral. And outside of the nucleus, we have the electrons that are negatively charged. These were eventually determined to be true. Protons are very, very light, but protons are about 2,000 times heavier than electrons. Remember that. Protons are about 2,000 times heavier than electron. However, the size of a proton is similar to the size of a neutron. Protons are about 1.007 atomic mass units in their mass. Neutrons are about 1.0087 atomic mass units. So protons are very similar in size to neutrons, but each of them is about 2,000 times heavier than electrons. And this is now what we call the nuclear model of an atom. This is still the model of an atom that we use up till today. An atom is mostly empty space, and the nucleus holds about 99.9% of the mass of the atom. Electrons are too light to be of any significance to the weight of an atom.